that you should be using. Cool. So yeah, next up, Matt D'Souza on TASTyTruffle.
Hi everyone, I'm Matt, and I'm from the University of Waterloo. I work at Oracle Labs now though, and I worked on this project with Jack, who's there in the back, and it's TASTyTruffle. So quick overview, because some of you are probably going to tune out at some point. The idea is that generics has to be implemented somehow, and sometimes that can have performance implications. A common technique used is erasure, and most people think of erasure and they think of boxing. So you have to box up primitives, and that's sort of the performance. When you think of performance, you think of that. But we argue that more generally, it sort of destroys type information that could otherwise be used by the compiler to produce more optimized code. And we show this by implementing TASTyTruffle, which is an interpreter for a subset of Scala, where we reify those types, and sort of demonstrate how having those types available allows the JIT to do more aggressive optimizations. So generics. Here's a sample method called swap, which takes an array and a value and sort of swaps a value into the array. Because that algorithm is not dependent on the type in the array, we can write it generically, and then we can use it for an int array or a string array or anything else you can think of. But then the question becomes, how does a computer run these code snippets? So monomorphization is what's typically done by C++, Rust, and some other languages. And the way that works is every time you use a generic definition with a unique set of types, we instantiate a specialization, like a new copy of the code. And that copy has precise types, which allows it to be more aggressively optimized. One trade-off, I guess, is that you have to create multiple copies of the code and pass them around in your binary. But an alternative approach, which is used by Java, Scala, and some other languages, you just erase it. You forget that it's generic. So you see there's no T up on the board anymore. And what you replace it with is some common sort of supertype that all generic values have to conform to. In the case of Java and Scala, that's object. But one consequence of this is that not everything can be used in a generic context. For instance, a primitive value like an integer doesn't fit. And so how do we make a round object fit into a square hole? We box it up. And so this has a performance implication because you have to allocate objects at runtime to deal with primitives, which is kind of defeats the purpose of using primitives, right? Another issue, which we find more fundamental, is that we've lost information about the program. We lost the fact that the value is of the same type as the element type of the array. And so the JIT has to sort of try to recover this info, and it sort of maybe makes its job harder for optimization. Another issue, actually, is that this primitive array actually can't be used, so this will fail to compile because you can't pass a primitive array somewhere where an array of objects is expected. And this is where Scala, in particular, deviates from, say, Java. It allows an array of T to be either an array of objects or an array of primitives, which allows you to avoid sort of allocating new collections anytime you want to pass an array into a generic context. But it doesn't come for free. What happens is the compiler rewrites any array accesses to use these accessor methods. And what are those doing? They're just doing runtime type checks. So I think in the Scala docs, they mentioned that it's a 2x or something slowdown, maybe 4x even. So it's not ideal for performance. Just a background about how Scala is typically implemented. What you do is you compile your Scala source to JVM bytecode, which is then executed on a JVM. This bytecode has erased types because the JVM doesn't understand generic types. It doesn't support it. So we thought, why not change the bottom half of this picture? Instead of executing JVM bytecode, we execute tasty. I'll get into what that is, but it has full type information. And it's a different representation of Scala programs. And we execute it with a truffle interpreter on top of the JVM with Graal. And this is where we sort of implement our support for generics. So tasty is a typed AST representation of Scala. That's what the name is, where it comes from. And it's emitted by the Scala compiler before erasure, which means we still have all the generic type information around that we need. And it has all the information we need to interpret a Scala program because it's very close to Scala's source. But like I mentioned, every definition, every expression in tasty has a type annotation. So when a value is generic, we can see that because of the types encoded in tasty. And we can use that to support heterogeneous sort of generic representations. And Truffle, for those of you who aren't familiar, you've seen a lot of Truffle talks so far. It's a framework for writing self-optimizing AST interpreters. And basically you get a language compiler sort of for free because of Graal with partial evaluation, where it basically does really aggressive inlining with respect to a particular AST. So you could think of this implementation as having 3 different parts. The first is just implement an interpreter for the subset of Scala that we're dealing with without support for generics. And that's pretty typical of Truffle, so I won't get into that. But next step is how do we support different heterogeneous values for generics? And this means passing in a primitive int into a context where normally it would be boxed up, but we can avoid that if we support heterogeneous representations. For that, we need to reify types, and then teach our AST to sort of deal with heterogeneous representations and understand, okay, in this case, I'm dealing with a primitive int array. This case, I'm dealing with an object array. And then finally, we found that this alone sort of led to some performance issues. So we need to make it perform well. And for that, we just needed to add dynamic specialization, which I'll talk about. So the overall goal, I guess, is to take that type parameter t and pull it into the method. It's now a formal parameter that's going to get passed around and into generic contexts. And then at the call site, what we do is we compute a type as another argument and sort of pass it in, and then let the generic method deal with it and use it when it needs to. To do that, we need to augment the AST at these call sites with type information. And because we have tasty, all that information is actually available for us. All we need to do is sort of pull it out of the tasty representation, and what we do is we create a type node, which is like a truffle tree. And it's very, I guess, obvious how you would go from one to the other, so I won't really talk about it. But the important part is that when you execute such a node, you get a shape, a runtime representation of a type. And that's what the reified type that gets passed around is. So once we have these reified types, these shapes, how do we use them? And here I'll give you a pretty typical example. This is an array apply node, so it's going to read a value out of an array. So what it does is it has a type node, like I said. We've added this sort of extra node to the AST. We execute it to obtain a shape, and then we use that to figure out what the representation of the generic array is, and then execute it that way. So for instance, when we execute the type node and get int back, we know that the array that we computed using the array node is a primitive int array. We can cast it and pull the value out. I've desugared the truffle because it's a little too complicated to explain, but this is sort of what you get out after compilation with Truffle. Like I said, this works, but it has some performance implications. I guess performance difficulties is a better word. And the reason for that is because you see here there's a lot of if, else if, and that's difficult for a compiler to optimize because you have sort of branches and merges. And along each branch, you might have very sort of specific info about the values in your program. But after the merge point, after you merge from this if, else, the compiler can't really retain all that info. It sort of has to destroy it because it takes like the union of all of those. So it makes it really difficult for a compiler to optimize this. Thankfully, in some cases, if your code is monomorphic, because of profiling, we might be able to say, oh, we only ever see the int case, emit it directly, and then we avoid the branching altogether, which is great. Or because these are nodes, we could have partial evaluation figure out that, oh, this node just computes the int shape. It's never going to compute anything else. And we can use partial evaluation to do this for us. However, generics are meant to be used with multiple different types. So it's more likely, and it isn't common in some cases, that you don't have a monomorphic type profile. You might have one with a few different types. And so you still have this branching. If we visualize that as like a control flow graph, we have this split and merge, which, like I said, is the problem with that compilers struggle with. And if you take a generic program and you sort of look at the whole control flow graph, we have it repeatedly. We're branching and splitting, branching, splitting. So how do we deal with this? Before we get to that, I should say that sometimes the compiler is able to optimize around that, and it has its own forms of optimization to deal with the polymorphism there. But on some benchmarks, it just wasn't able to, and usually it correlates with the more complex benchmarks. So the way that we solve this is by duplicating the code, which is what the compiler normally does. It has a code duplication pass, but as you saw on the previous slide, it can't do it reliably. Sometimes it does it, sometimes it doesn't, because it's based on heuristics, and the bigger your program, the more sort of candidates you have, so I guess it makes it difficult for the compiler to figure out. But what we do is we duplicate it ourselves. And so what we do is make a new copy of the AST dynamically for each set of type arguments that we use the generic code with. And what we get out of that is because, say, in this int branch, we know that t is int. That means we can fold away all the subsequent checks because they're going to be constant. The t is going to be a constant in each branch. And we end up with a very straight line monomorphic code that the compiler can optimize. I think the cool thing about this is that it's dynamic. We didn't need to statically transform the AST. It's all done because of Truffle's profiling and partial evaluation. We had an earlier iteration of this work where we transformed the AST and we walked it and said, take t and fill in int for it. But it turns out that we didn't actually need to do that. We can sort of get it for free with Truffle's dynamic specialization and dead code elimination. So here are the results. On the top, we have the polymorphic workloads. On the bottom, the monomorphic ones. And the first two graphs, the bars, the blue and orange, are JVM interpreters on Hotspot and Graal. And the second two, the green and red, are TASTyTruffle without specialization and with. And so what we found was that on the polymorphic workloads, TASTyTruffle with specialization is able to outperform the rest of them. And I'll talk about on the next slide why that is. And on the monomorphic workloads, it sort of just ties GraalVM. And the reason for that, we suspect, is just that when it's monomorphic, there's already type profiles in the JVM bytecode. And so when you're speculating that something is monomorphic, it doesn't really give you a benefit to have the types in the tasty representation. And because it's an interpreter, an AST interpreter, it does take a little longer to warm up and it uses a little more memory. But part of that is because the mechanism to parse tasty actually calls into the Scala compiler libraries, so you're pulling in the whole compiler, and it's, maybe there's a way around that, I'm not sure, but it's not inherent to our technique. So discussion. These are some of the reasons we found that TASTyTruffle is able to outperform the JVM-based implementations. The first is that the duplication is done less reliably on Graal than TASTyTruffle. And of course, it's always reliable on TASTyTruffle because we do it ourselves. But with Graal, it sort of has to speculate, like, oh, should we duplicate the code here or here or here? And it can't always make the right decision. So you could think of this as making the compiler's job easier. And another thing, like I said earlier, we understand the type associations between different values. So if we figure out that t is int, and that means we know that source is in primitive int array. And we also learn that destination is a primitive int array. On the JVM, it just sees objects. Once it figures out source is an int array, it doesn't know anything about destination and has to do some extra work to figure it out. These type associations don't have to be explicit. They could be implicit ones. So for instance, in Scala, you have these things called given instances, which are like type classes. So say you want to figure out how to sort values of type t, you pass an ordering type class. Because we keep separate type profiles for each of the types t that we use, each of them usually has like a monomorphic or maybe bimorphic call site for all of those calls to these type classes, and usually Graal can then devirtualize those calls. And there's more in the paper. One thing I found especially sort of interesting was that in these JVM implementation, when you have to call these Scala accessor methods, they actually use a single global profile. So we were able to sort of do some weird things and pollute the profile in really weird ways to sort of arbitrarily degrade the performance on the JVM benchmarks. So just to recap, Erasure is problematic for performance, but it's not just about boxing. So we showed that by interpreting a non-erased representation, tasty, we were able to reify types, support heterogeneous representations, and empower the JIT to sort of produce more optimized code. Thank you.
Thank you. So we get some time for questions. Okay. Hold up.
Hello, thank you for your wonderful talk. And my question is that how would you compare your non-type erasure approach for the generic types with the .NET implemented one, which is I think might be the most well-known non-type erasure generic type within some JIT environment?
Sorry, I missed that. Could you repeat that?
The .NET CLR.
Oh, yeah. We didn't really look at CLR. We know that in C# they do something similar, but we sort of just focused on Scala here. I think they do something similar where they reified at runtime, but I couldn't tell you much about it beyond that. I tried looking at papers, but I couldn't find much.
Okay, thank you.
Can you take one? Yes. Yep.
Hello, I'm Alex. I work with Martin Uderski. I just have a minor question. Do you interpret all of Tasty?
No, just a small subset. It's described in the paper. I think a big problem is that because Tasty is emitted before Erasure and before all these other lowering passes, it's like a big implementation effort to interpret that, because I think pattern matching and all these other constructs are not yet lowered.
Okay. Yes, it is. Okay, let's chat after.
Thanks.
Okay. Thank you, Matt.